Hello everyone. I am from China. It is my honor to attend this SMC 2024 conference, and I will try my best to present my paper. The title of my thesis is An Efficient Token Mixer Model for Sheet Metal Defect Detection. I will present my paper from 4 aspects, namely Introduction, Method, Experiment and Conclusion. Part 1. Introduction. Surface defect detection on metal sheets is a critical aspect of quality control in industrial settings, essential for ensuring production safety. However, the inherent nature of manufacturing processes inevitably leads to the production of defective items. With the ongoing advancement of defect detection technologies, conventional machine vision techniques have found widespread application in detecting surface defect on metal sheets. Wang et al. Introduced a novel method for template creation, leveraging statistical features and sorting operations, achieving an average detection rate of 96.2%. Song et al. Employed a scattering convolutional network based on wavelet transform to detect surface defect on hot-rolled strip steel, achieving a detection accuracy of 98.6%. Despite significant improvements over manual inspection, traditional machine vision detection methods still exhibit certain limitations. Part 2. Methods. The structure of the proposed SATR-net model is depicted in Fig. Firstly, after inputting the image, the convolutional layer is used to adjust the image size and channel, and then the STR module and the lightweight scatter module are employed to extract feature information. Secondly, following the multi-scale design concept, the GCD module is employed to fuse feature information for extracting small defect. Finally, the feature information is fed into the detect module for defect detection. Subsequently, detailed descriptions of the 3 modules, namely STR, SCATR, and GCD, will be provided. Convolutional neural networks effectively capture the local features of images by leveraging the characteristics of local connections and weight sharing. However, traditional convolutional models often struggle to effectively handle global information, such as slender scratches on the surface of metal sheets. Therefore, we introduce the self-attention mechanism of VIT to enhance the extraction of global information. For close-range images like those in the metal sheet dataset, the defect shapes undergo minimal changes and exhibit a single color, resulting in a large number of redundant features during model feature extraction. If the transformer module is employed for feature extraction, it encounters the same issue, where a large amount of repetitive information is highly likely to interfere with the model's selection of a small amount of other useful information, thereby impacting detection accuracy. Therefore, we propose the novel sparse self-attention method, and the model structure is shown as BSA in Fig. This structure designs a bottleneck token in the multi-head self-attention of VIT, and introduces the bottleneck block into the token to extract the most representative and more abstract features in the input data in a dimensionality reduction way. Based on the above idea, this paper performs proportional sparse operation on Q, K, V variables in transformer, and determines the sparse factor by the location of the module and the total number of layers of the backbone network, so as to determine the proportion of feature sparsity Y and reduce the interference of redundant features on the model. The model structure introduces a novel soft attention mechanism, SCA, to replace the multi-head self-attention mechanism in VIT. Additionally, the model adheres to the general architecture of metaformer. The MLP layer maps original features into a new high-dimensional feature space through 2 fully connected layers, enhancing its capability to capture nonlinear relationships between features. Our design of SCA soft attention is flexible and lightweight, capable of capturing long-distance dependencies within a single channel while preserving precise location and spatial information. We utilize SCA soft attention as a token mixer to address the challenges posed by the relative complexity and heavy computational burden of self-attention. This approach significantly improves the accuracy of model detection while ensuring that the model maintains lightweight performance to meet the real-time requirements of devices with relatively low computing power. We have devised a novel bottleneck convolutional structure named GCD, and the corresponding model architecture is depicted as the GCD module in Fig. Firstly, we process the input data through grouped convolution with a 3x3 convolution kernel, aiming to reduce the number of parameters and enhance the learning and generalization abilities of the model. Secondly, drawing inspiration from the bottleneck structure design, we utilize standard convolution for cross-channel information interaction, reducing and restoring the dimensionality of the input feature map. Additionally, we employ depth-wise separable convolution with a 3x3 kernel to extract spatial feature information, enabling the model to better capture image features across both space and channels. Finally, we applied residual connections to GCD structures to enhance performance, improve gradient propagation across layers, and capture multi-scale features. Part 3. Experiments. We utilize the publicly available NOI-DET dataset for steel surface defect and an industrial-grade aluminum surface defect detection dataset as our research data sources. The steel dataset provided by Northeastern University comprises 1,800 grayscale images, representing 6 typical defects, with 300 samples for each defect, such as patches and scratches. The industrial-grade aluminum surface defect detection dataset consists of a total of 400 grayscale images, featuring for typical defect, pinholes, scratches, wrinkles, and dirt. The experiments were conducted on a Windows system with PyTorch to 2.2, CUDA 12.1, and CUDNN 8.8 configurations. The GPU utilized was an NVIDIA GeForce RTX 4060. We employed the SGD optimizer with an initial learning rate of 0.01. Table I presents the comparative experiments of our proposed model, SaturnNet, with existing models on the NOI-DET dataset. Currently, mainstream detection models such as YALO V8, PPYOLO, and PicoDet have demonstrated high performance in the field of defect detection. Building upon this foundation, our model achieves further improvements. Experimental results indicate a respective increase of 4.6% and 4.5% in detection accuracy and recall compared to YALO V8, and an increase of 3.2% and 4.4% in MAP 0.5 and MAP 05 0.95. Relative to mainstream industrial models like PPYOLO and PicoDet. Our model exhibits significant enhancements in detection accuracy, recall, and mean average precision. Table presents a comparative analysis of our proposed SaturnNet model with existing methodologies on an industrial-grade aluminum surface defect detection dataset. Our experimental findings reveal the superior performance of our model over PPYOLO and PicoDet, demonstrating improvements of 4.7% and 5.0% in detection accuracy and recall, respectively, compared to PPYOLO, and 3.0% and 3.3%, respectively, compared to PicoDet. Additionally, our model achieves enhancements of 5.6% and 4.6% in MAP 0.5 and MAP 05 0.95, respectively, compared to PPYOLO, and to 0.9% and 3.5%, respectively, compared to PicoDet. Notably, our model surpasses mainstream industrial detection models on publicly available aluminum datasets. In our study, we used YALO V5s as the baseline and performed ablation experiments with multiple improved methods based on NOI-DET dataset. Experimental results show that different methods have significant effects on the improvement of detection performance. Specifically, the STR method achieves an impressive accuracy improvement of 79.3% by introducing a novel feature extraction strategy. At the same time, The scatter method not only maintains a good detection accuracy, but also effectively reduces the number of parameters of the model, thus improving the computational efficiency of the model, which is of great significance in practical applications. The GCD method performs well in the recall rate and MAP 0.5, which further improves the detection ability of the model in complex scenes. With these improvements, our overall model performance improves significantly, increasing the detection precision from 75.7% to 83.5% from the baseline, and the recall from 74.8% to 82.4%. In addition, MAP 0.5 and MAP 0.95 are also increased by 2.4% and 3.6%, respectively, compared with the baseline, indicating that the comprehensive ability of the model on multiple evaluation indicators has been enhanced. More importantly, despite the significant improvement in performance, the number of parameters of the model is slightly reduced from 702M to 698M, which means that our improvement not only improves the detection effect, but also reduces the consumption of computing resources to some extent. Part 4. Conclusion. Defects such as scratches, patches, and cracks frequently occur during sheet metal production. However, the low detection accuracy and slow processing speed of industrial defect detection models significantly impede enterprise production efficiency. The aforementioned issues primarily manifest in three aspects. Firstly, the model complexity and computational overhead are substantial. Secondly, detecting small local defect poses a significant challenge. Thirdly, extracting global features, such as elongated scratches, proves to be difficult. To address these challenges, this paper introduces a novel network architecture called SAT-RNet. Firstly, within the model backbone, the STR module is devised through incorporation of the sparse self-attention method and the CNNS parallel vision transformer model in the shallow layers. This module significantly enhances the model's capability to extract global features. Secondly, the scatter module is designed in this paper by substituting self-attention with the designed SCA soft attention as the token mixer. The module aims to enhance detection accuracy while reducing the number of parameters, thereby fundamentally addressing the problem of model complexity. Finally, this paper presents the GCD bottleneck convolution module. This module combines shallow and deep features, enabling the fusion of more information beneficial for detection, thereby achieving improved efficacy in capturing minute targets. Experiments demonstrate that SAT-RNet surpasses existing advanced models in detection accuracy on public datasets. Thanks for watching.